Uh, Her work has been presented at 7 top-tier international conferences and has led to more than a dozen research manuscripts, out of which 8 are currently published in top-tier international journals. She has been a Vishweshwara PhD fellow during her PhD at IISc. Her research interests include quantum error correction codes, fault-tolerant quantum computation, quantum circuit architecture, quantum algorithms, and quantum communications. She has served as the chair of IEEE-IISc Communication Society Student Chapter, the corresponding secretary at IEEE-IISc HKN Chapter, and the secretary of IEEE-IISc Women in Science and Engineering Affinity Group. She has received the Best Researcher Award uh, in IISc in the IEEE Bangalore Section Mission 2020 Challenge. She also received the IEEE-IISc Outstanding Officers Award in 2020. She is a member of IEEE HK. I extend a warm welcome to Dr. Priya Nadkarni.
Thank you, Praveen.
You may share your screen.
Is my screen visible?
Yes.
Yeah, so thank you, Praveen, for the lovely introduction. Good morning, everyone. So today, me and Praveen will be giving you a basic introduction into quantum computing and quantum computing algorithms. Praveen?
Yes. First, what is quantum computing? So the systems in which computing is performed, these systems take advantage of the laws of quantum physics. Compared to what classical computing does, we use physical systems, but we discretize them and use them classically. But here we take advantage of the quantum nature and make use of this to improve a computational power. So these physical systems allow two major phenomena called superposition and entanglement. So superposition and entanglement together can be composed to form this paradigm called quantum parallelism, which leads to a lot of advantages. The motivation to study this field is the main thing is the quantum parallelism. Quantum algorithms can be efficiently performed when compared to classical methods. The quantum simulations of biological and chemical systems are pretty efficient because the biological and chemical systems themselves are quantum and display such non-classical phenomena. Quantum sensors are known to have better sensitivities and they can be fine-tuned to improve measurements. Ultra-fast secure quantum communication can be achieved using quantum technologies, which are physically secure, whereas classical systems are information theoretically secure. Next slide. So before we proceed with the basics, let's talk about the current state of the art and what's right now in research. Physical systems like photonic circuits, ion traps, superconducting circuits, etc. Even topological systems are being explored. And these all are various quantum systems which display quantum properties are used to perform these computations. For example, Xanadu and PsiQuantum are developing a system called photonic quantum system, which uses photons and mirrors, beam, reflectors, etc. IBM and Google are developing superconducting quantum computers, which rely on silicon-based systems. IonQ and Honeywell are developing ion trap-based quantum computers, and Microsoft is working on topological systems, which can be used to perform quantum computation. Quantum computation for quantum communications, photonics is preferred technology because you need to transmit it to a long distance. Quantum dynamics is linear. Just a minute, I'll answer the question in the chat. But before that, so quantum dynamics is linear, and hence using linear algebra, small quantum systems can be simulated approximately, like I described earlier, yesterday. Some Python-based simulators are Qiskit by IBM, which will be detailed in the tutorial today. Search by Google Quantum, and Tiny plus Strawberry Fields by Zanuda. Mr. Tilak's question, ultra-fast quantum communication. It is not faster than speed of light. Any communication cannot be faster than speed of light. By what we mean by ultra-fast quantum communication, it is in the like it will be using systems similar to uh, optical fibers, which is pretty fast. So that's what I mean by ultra-fast. It's not faster than speed of light. I'm sorry if there's small misunderstanding. Next. So the quantum stack, basically, this diagram is very similar to the classical stack, where we want to illustrate the various steps and processes in building a quantum computer. So first, we have something called quantum complexity theory, which is basically a very theoretical, abstract theoretical way to determine the efficiency of an algorithm or a computing method, which is not of relevance right now. So the quantum algorithms are the high-level ways that how we understand how we can make use of the computing power of quantum computers. Then the quantum programming level has three things: the architecture of our algorithm implementation. Say you have a circuit-based algorithmic implementation of some certain algorithm which gives you some advantage. You compile it such that you can map it back to the circuits in the actual quantum hardware. So quantum hardware may not be completely connected, so you need to remap it. So this is on top of programming languages where these programming languages are like, for example, compiling the quantum circuits to the specific hardware which we need. Besides this, you have the quantum error correction theory, and this theory is required because the quantum systems are usually error prone. For example, they undergo decoherence, bit flips, and phase flip errors. So hence, we need error correction for quantum systems to make them fault tolerant. So this combined with the input algorithms and with the software can be used to efficiently implement some algorithms. Then below this is the implementations of our quantum error correction codes, which are implemented such that the system is fault tolerant. And fault tolerance will be talked in lecture 2. So now next we have below this we have the technology building block, which is the very basic block, which talks about how exactly the circuits are mapped and more hardware specifications. Next slide, please. So before we proceed to quantum communications and computation, so classical computation and communication, let's see what happens. You basically have an input state, which when you apply an operator, you get an output state, which is very similar to the classical system also. So for classical systems, I have input bits of information, which is either 0 or 1. And this is a binary bit of information. So input and output states, either one bit of information or a multiple bit of information. A multiple bit of information usually called a register. So they can be represented as a vector of bits, b1, b2 till bn, and this belongs to the field f2n. So basic operations are the bitwise additions and multiplication operators. So XOR and these are basic classical system gates which you would have heard of. And you know that XOR and NAND, NOR, etc. form universal gates. That is, any computation, any classical computation can be executed with these gates alone. So measurements do not affect the value of bits. They give you a definite value, and after measurement, the state is the same. Now let's go to quantum states and see how different it is from classical states. So here we had earlier seen the classical units of bits of information are either 0 or 1, but a quantum bit can be both 0 and 1 at the same time. So if you represent state 0 with the vector 0, state 1 with the vector 1, ket 0 and ket 1, the superposition can be written as a linear combination of the state 0 and the state 1. Here, A and B are complex in general. So this is the C2 space, the Hilbert space of dimension 2. And here we can, as I had described yesterday in the tutorial, the ket 0 can be written as a column vector 1, 0, and 1 can be written as a column vector of 0, 1. Here, A and B are uniquely defined by the superposition. The two-dimensional vector. So thus, the two-dimensional vector in this Hilbert space can be written as A comma B. So the bracket notation, as I had introduced yesterday, can be used to represent this vector. And its dual, the bra, this is the ket psi, this is the bra psi, and the bra psi can be is the Hermitian conjugate of the ket psi, and Hermitian conjugate is obtained by taking first the complex conjugate and then transposing the vector. So we had seen that in a classical system, measurement does not affect the state of the system. Say if the bit was in state 0 first and you measure it, it collapses, it's still in 0. But if it's a quantum system, if I have the state A0 plus B1, if I measure it in the standard basis, say 0 and 1, I will either get a measurement outcome of 0 or 1 with the probability of A square plus B square. And the final state will be 0 or 1 based on what I obtain. So the final state will be a classical state and the superposition will be lost. Since these represent probabilities, the mod A square, mod B square, the probability should add up to 1. They should be normalized. There's a small question. What's the significance of the A and B being complex? So A and B are complex mainly because the quantum systems follow this math. So there is no other physical significance. And because they follow these math, they also allow us to give something called a quantum phase, which we'll be talking about later. So to answer your question very briefly, these quantum systems follow, these quantum states belong to Hilbert spaces, and they follow such dynamics. So because they follow such dynamics, we can represent them by these complex vectors. And because of this math, they also give rise to something called quantum phase, and which is a complex phase, which is a result of such a complex coefficient. Next slide, please. So an example of superposition, let's consider the state plus, so 0 plus 1, 0 plus 1 by root 2. So when we measure the state plus in the standard basis, we obtain the measurement outcome 0 with probability half. So mod A square is 1 by root 2 square, so we get half. And probability of 1 is half, similar to 0. So the state of yes, as Mrs. Nalli has pointed out, so to cover the full sphere of the Hilbert space, we use complex notations. So the quantum systems inherently follow mathematics which are based in quantum space, which are based in Hilbert spaces, and thus we require complex notations to span the entire space. So the state of the qubit post measurement will be either 0 or 1. It won't be the superposition state. So the measurement results in the state 0 minus 1 by root 2 is also similar to the state plus. They give the same probability outcomes when measured on the standard basis, but they're not the same. They're not the same. Plus and minus states are not the same. So we will be talking about this later. Dr. Priya.
Yeah. So based on all that, what Praveen explained, there's a quantum mechanics postulate regarding the state vector. So this is the first quantum mechanics postulate. So what this says is that associated to any isolated physical system is a complex vector space with inner product that is a Hilbert space known as the state space of the system. This is what basically Praveen explained, that with every quantum system we have a associated vector in a Hilbert space, and this vector is known as the state vector, which is a unit vector in the system state space. So the state vector for our state psi was AB transpose, and the inner product which is spoken about here, it's basically the complex inner product. So if we represent if we have two states, psi1 and psi2, and we take their inner product, the complex inner product, by conjugating the elements of psi1 and then taking the inner product with psi2, then we use this inner product in our Hilbert space. So this is the first quantum mechanics postulate. So Praveen explained about the quantum states. So that was only for one qubit. So what happens when we have multiple qubits? How do we represent the quantum state at that time? So in the classical case, we had a vector where each value of the vector was a bit. But for the qubit case, when you consider n qubits, the state is basically obtained by, again, a superposition of basis states. So here these basis states are obtained by taking the tensor product of the basis states of the individual qubits. So for example, what I mean by this is that let's consider a two qubit state. So any two qubit state can be represented by initially taking the basis states. So we take we take the basis states for individual qubits. So let's take 00 or 01 or 10 or 11. We take the tensor product of 0 and 1s to obtain these basis states, and then we take a superposition of all these basis states, and we can represent any qubit in a superposition of all these basis states. So where all these coefficients are complex number, and again the vector which is obtained from the coefficients is a normalized vector. For example here, like what do I mean by 0, 1 over here? 0, 1 is nothing but the tensor product of 0 and 1. So in like Praveen explained, 0 we represented by 1, 0, and 1 we represented by 0, 1. So when you take the tensor product of this state, we obtain this particular vector. And similarly, we obtain all the four vectors, and we will be obtaining the state vector for a two qubit state. So based on this, we have a quantum mechanics postulate regarding composite systems. So what does this postulate say? It basically says the state space of a composite physical system is a tensor product of the state spaces of component physical systems. Moreover, if we have systems numbered 1 through n, and the system number I is prepared in the state psi I, then the joint state of the total system is psi1 tensor psi2 and so on till psi n. So here individual systems are initially prepared and then put together. But if we apply an operation on the composite system as a whole, then it need not just be in the tensor product form. We can even get a superposition of the states like we saw in the previous slides. So with that, we saw about quantum states. Now let's learn about the quantum operations or quantum gates. So how do we represent these quantum operators or quantum gates? So as we saw before, quantum dynamics is linear, and we saw the states were represented as vectors. So this basically means that we can represent the operators using linear algebra, where we basically use matrices. Hence, the operator M would be a matrix, but we also saw that all these quantum states, they're normalized states. This basically means that this leads to quantum operators being unitary operators. So what does unitary operators mean? Let's take a matrix U. Then U is unitary if U dagger equals to U dagger U equals to identity, where U dagger is the Hermitian conjugate of U. And because U dagger is the inverse of U, a reversible computation is possible. So quantum computation is basically reversible when we use unitary gates. And to summarize both states and operators, states are basically normalized two-dimensional complex vectors for a single qubit, and the operators that operate on it are unitary 2 cross 2-dimensional complex matrices. And yeah, one note is about the unitary gates on a superposition. So let's say we have a unitary gate and we apply it on a superposition. Then U applied on A0 plus B1 is same as first computing U0 and U1 and then taking the superposition of them. So it's enough to just study the how the gate acts on the basis qubits. So that's what we'll be seeing from now on. So before moving on to see what are the various gates, let's look at this quantum mechanics postulate on unitary evolution. What it says is that the evolution of a closed system is described by a unitary transformation. That is, the state psi of the system at time t1 is related to the state psi dash of the system at time t2 by a unitary operator, which depends only on the time t1 and t2. So even the evolution of a quantum system is unitary in nature. So next, let's look at the unitary gates. So the first gate that we'll be learning today is the X gate. So this is also known as the bit flip gate. It's very similar to the NOT gate in the classical case. So here we have X represented by this matrix of this from this 2 cross 2 matrix. So what X does is when it operates on 0, it flips it to 1, and when X operates on 1, it flips it to 0. That's why it's called the bit flip gate. And this is the graphical, like a diagrammatic representation of it. Let's next look at the eigenvalues of X, which we'll be needing later on. So here, when X operates on the plus state, it does not change the state. So hence, the plus state can be seen is an eigenstate of X with eigenvalue 1. But when X operates on the minus state, then we get minus of the minus state. So it basically means that the minus state is an eigenstate of X with eigenvalue minus 1. Next, let's look at the Z gate. So the Z gate is similar to the bit flip gate, but here it flips the phase, not the basis state. So the Z gate is given by this particular matrix over here. And when Z operates on 0, it doesn't do anything. It retains the state as it is. But when Z operates on the ket1 state, it introduces a phase over here, or it flips the phase. Like the phase initially was +1, now it becomes -1. And hence the gate is called the phase flip gate. So again, diagrammatically, we are representing it as shown in the figure. And the eigenvalues over here. So just looking at these two equations, what we see is that 0 is the eigenstate of Z with eigenvalue 1, and 1, ket1, is the eigenstate of Z with eigenvalue -1. Yeah, the next gate is the Hadamard gate. So the Hadamard gate is given by this particular matrix. If you're aware of DFTs, then this is a 2 DFT. And so what this particular matrix does is that it transforms the X gate to the Z gate and Z gate to the X gate on conjugation. When the Hadamard gate is applied to the state 0, we get the plus state, and when Hadamard gate is applied to state 1, we get the minus state. And when we take, like if we take n qubits, each in state 0 initially, and we apply Hadamard gates to each of these qubits, then we get an equiprobable superposition of all the basis states. So this would be useful later on when we are learning about quantum algorithms. The next gate is the phase gate and the pi/8 gate. So phase gate is also called as the S gate, and the pi/8 gate is called as the T gate. So here the S and T gate, what they do is when they operate on the 0 state, there is no change. But when they operate on the ket1 state, then they introduce a phase over here. And here the phase for the S gate is the complex value of I, and for the T gate it is e power I pi/4. You might be wondering, like, why are we calling this the pi/8 gate and not the pi/4 gate? It's because if we take out a common factor e power I pi/8, we get this particular matrix. And this common factor, it's a global phase which we cannot view, so which we cannot observe. So we can just neglect that, and we can just look at this matrix. So this particular matrix is basically rotates the state on a Bloch sphere in the z-axis by pi/8. So what is the Bloch sphere? We'll learn about that soon. The next gate is the swap gate. So swap gate is similar to the classical gate. It basically swaps the states of 2 qubits, and it's represented by this notation. The next gate is the C0 gate. So C0 gate is also called as the control NOT gate. So this is a 2 qubit gate. I mean, the swap gate was a 2 qubit gate, and the rest of the gates were the single qubit gate. So what control NOT gate does is it has one of the qubits as the control and the other as the target. And if the state, which the first qubit, let's say the control qubit, is in state 0, then it does nothing. So when C0 operates on 0, 0, it does not do anything on the second qubit. But when the control qubit is in state 1, it flips the other qubit. So 1, 0 is flipped. The second qubit is flipped from 0 to 1 and from 1 to 0 when the first qubit is in the state 0. Similarly, we have the Toffoli gate. So Toffoli gate is similar to the C0 gate, but here we have 2 control qubits, and the flip takes place on the target qubit only when both the control qubits are in state 0. So only for these 2 states because the first two qubits are in state 1, the target qubit is flipped. In the rest of the cases, that's not the case, and hence no operation is performed. Okay, so those were the set of gates, set of quantum gates. There are many more, but we'll be learning a few more in the tutorial called as rotation gates. So let's now look at the universal set of gates. So in the classical circuits, we know that using certain universal sets like NAND gate or NOR gate, we can implement all the circuits. So here, similarly, we have a universal set of gates. So these are four universal sets of gates. So the first set is basically all the single qubit gates and the CNOT gate. The second set is the Toffoli gate and the Hadamard gate, but when specific quantum states are available as inputs. The third set is the rotation gate and CNOT gate. And the fourth set is the CNOT gate, the Hadamard gate, S gate, and the T gate. So now when we look at all these unitary gates, I mentioned that using just these unitary gates, we can like construct any quantum circuit, which means we can implement all the quantum operations using this. But when we put all these quantum operations together and see, they form something called as a unitary group. And this group is a subspace of, it's a subset of the complex space of matrices, but this group has infinite number of elements. If we want to work with these elements, we would need some finite set to work with. One is obviously the standard basis of the two by two set of matrices, but there's one more unitary basis called as the poly basis, which is widely used because each element is unitary in nature. So here the poly basis has four elements. The first is the identity element itself. The second is the bit flip operator, which we saw before. The third is the phase flip operator, which we saw before. And the fourth is the Y operator, which is a combination of the bit flip and phase flip operators. So using all these four elements, all the quantum operators can be represented. And if we look at the group which is generated by all these four elements, it forms a group called as a poly group, which we widely use in when we are working with quantum systems. So the poly group basically has all of these elements plus the coefficients are just plus and minus 1 and plus and minus I are added in. And the all these poly operators, they satisfy these properties. So all the poly operators are Hermitian, they're their own inverses. And the non-identity poly matrices, they have zero trace and the determinant is 1 and they anti-commute with each other. Also, poly operators are orthonormal with respect to the normalized trace in a product. That is basically this particular in product. So this is nothing but an orthonormal basis. Okay, so that was about operators. Now next let's look at measurements. So Praveen explained initially that if we measure the state A0 plus B1 in the standard basis, that is 0 and 1, then we get measurement outcome to be 0 with probability mod of A square and measurement outcome to be 1 with probability mod of B square. But is this the only form of measurement? Well, no, there are various other forms of measurement. In general, we can choose to measure in any orthogonal basis state and we can obtain different results. So for example, we can choose to measure the state in the plus minus basis. So again, plus minus is again an orthonormal basis. So we can measure in this. So the measurement outcome is plus with probability A plus B by root 2 the whole square. And it's minus with probability A minus B by root 2 the whole square. So how do we get these probabilities? Well, that we learn next. So there's a quantum mechanics postulate based on measurements again. So here we have, what does this say? It says that quantum measurements are described by a collection of measurement operators. So every quantum measurement is associated with a collection of operators. And these operators acting on the state space of the system being measured, these are operators. The index M refers to the measurement outcomes that may occur in the experiment. If the state of the quantum system is psi, immediately before the measurement, then the probability that the result M occurs is given by P of M, psi, MM dagger, MM psi, and the state after measurement is this state. So using this, we can obtain this result. And if this seems a bit complicated, then let's look at projective measurements, which is the majorly we use these kind of measurements. So in the projective measurements, this observable or the operator M, which was spoken about, this is a superposition of projection operators, basically projections onto certain eigenspaces of an operator. And each of these operators, like for example, if we can look at observable x over here, then the observable x is a superposition of these two projection operators, that is plus plus and minus minus. So this projection operator projects the state onto the plus state, and the other second projection operator projects the state onto the minus state. And these lambda i's are called as the eigenvalues of this observable m. So it can either be +1 or -1. And this is equivalent to a plus minus basis measurement. This is just the term of observables is just another way to refer to measurements. So here, so that's the next thing about that. How do we refer to measurements based on observables? Because you might come across terms like measuring the poly x operator or the poly z operator. So what does this mean? This basically means that every measurement is associated with an observable, and this poly x or poly z are those observables, and the values observed are the eigenvalues of the observable. So if we consider O psi equals to E psi, then E is the eigenvalue of O, and whatever measurement outcome we get, it's basically this eigenvalue, whatever we observe on the measurement device. And as all the only real values can be observed, the observables are Hermitian in nature. So for example, when we say we are measuring the poly x operator, it basically means that we are operating in the 0 plus 0 1 basis, because those are the eigenvectors of the poly z operator, and the measurement outcomes are +1 and -1. Similarly, for the poly x operator, it's the plus minus basis. An application of these concepts of measurement is the quantum key distribution, which will be covered in lecture 3. So the next thing what we'll be looking into are the no-go theorems. So there are a couple of no-go theorems in quantum mechanics. So we'll just be looking at 3 of them. There are many more. So what does the first theorem say? It's called the no cloning theorem. It basically states that it's impossible to create an identical copy of an arbitrary unknown state. So this means we cannot use copy paste what we do in daily life in classical computers when we don't know what the state is. The next theorem is the no deletion theorem. What this says is that when 2 copies of an arbitrary quantum state is given, it's impossible to delete one of the copies. So this can be viewed to be the reverse of the no cloning theorem. The last one is the no communication theorem. It's what this basically says is, suppose we have a composite system, and we have 2 component systems, and we have one observer for each of the component systems. Then we cannot just perform measurement on one component system, and the observer in the other component system cannot just get the information in one component system. So although you might question about quantum teleportation requires a classical communication between the 2 observers or 2 component systems. So just using measurements, we cannot transmit the information. That's what this theorem says. Okay, so next is the physical phenomenon of entanglement, which Praveen mentioned about initially. So this, along with superposition, leads to quantum parallelism that leads to efficient algorithms. So this is a physical phenomenon which is unique to quantum mechanics. So when do we say that 2 states are entangled? What is entanglement exactly? So 2 states are said to be entangled when the state of one qubit cannot be described independently of the other. So this can be viewed as a form of correlation between particles, irrespective of the distance between them. They might be very close to each other, or they could be at the extreme ends of the universe and still be entangled. And also, entanglement cannot be created locally. That is, you cannot just perform some operation on one qubit and expect it to get entangled to some other quantum state. So an example of entanglement is the Bell state. So here the Bell state is 0, 0 plus 1, 1 by root 2. So here, let's just look at the first state. If we perform a measurement on the first state or first qubit of the Bell state in the plus minus basis, then the measurement outcome is +1, with the post measurement state being 0, 0 with probability half, and measurement outcome is -1, with the post measurement state being 1, 1 with probability half. One thing to observe is that although we just performed measurement on the first qubit, even the second qubit is collapsing. So hence the state is entangled, because we cannot describe the state independent of each other. And there are various applications of entanglement, like there's quantum teleportation, superdense coding, quantum error correction, etc., which we'll be learning in lectures 2 and 3. Okay, so we saw that when states are entangled, we cannot represent one state independent of the other state. So does this mean that we cannot represent them anyway? Because we'll at the end of the day have to work with such states, right? So one way to represent that is the mixed state. It's actually called a mixed state when a state is entangled to some other state. And the representations, there are two forms. One is the ensemble representation, where we represent the state as a mixture of uh, quantum states. So here we have this particular mixture where this basically means that the state psi1 occurs with probability p1 and so on, and the state psi-m occurs with probability pm. So for example, let's look at this Bell state as we saw the measurement outcomes before. This basically means that the first qubit of the Bell state is in state 0 with probability zero point 0.5 and is in state 1 with probability zero point 0.5. So this is how we represent the state as a mixture of uh, pure state. So whenever a state is not entangled to any other state, then it's called a pure state over here. The another representation of a mixed state is using density matrices. That is, we use a matrix to represent it. So similarly here, we consider the ensemble representation and we transform it to the density matrix representation by taking the Kedbra product of the states and multiplying with it with the probability value and summing it over that. So this is a matrix, and this is called as a density matrix. So this density matrix has certain properties, like the trace of this density matrix is 1 and the density matrix is a positive operator. And we'll be using the density matrix representation in various fields of quantum mechanics. So one such example is quantum information theory. Okay, so the next theorem is the Smith decomposition theorem. So what does the Smith decomposition theorem basically say? It basically says, let's have a composite system AB in state psi, then we can always represent the state psi as a superposition of tensor products of orthonormal states of the individual component systems, where the coefficient in the superposition are non-negative real numbers, and they satisfy this particular equation. That's what Smith decompositions says. Okay, so here we come to the Bloch sphere, which I was speaking about before. So if we have a state psi in A0 plus B1 state, then we can use some mathematical representations by replacing A by its absolute value and phase representations, and we can represent this particular state in a form as shown here in equation 33. So here we have e power I phi naught, which is known as the global phase, which we cannot observe, so we don't care about it. And then we have theta and we have e power I phi. So e power I phi is the relative phase, which Praveen will be speaking about shortly, and we have the cos theta by 2 and sin theta by 2. So if you look at this equation, because we don't care about this phase, this can be just represented in terms of phi and theta, and we know that the state is a normalized state. So we can consider the radius to be 1, and we can represent it in terms of a spherical coordinate system. So in the spherical coordinate system, we represent it by 1, theta and phi, and it can be any point on the Bloch sphere when it's a pure state. When it's a mixed state, because it's a mixture of states, it can be any point inside this particular Bloch sphere. And all the your single qubit operations can be represented by rotations on this Bloch sphere, of this Bloch sphere. So if you consider a point over here and you apply any unitary operation, it's a rotation in this Bloch sphere. 0 and 1 are represented by these 2 points on the Bloch sphere. Okay, so till now we saw about classical information and quantum information. So the information, the states transmitted, and the channels, both of this can be, all these three can be either classical or quantum. And based on various combinations of these, we can achieve different types of communication. Like if everything is classical, then it's classical communication. If everything is quantum, then it's quantum communication. But with various other like combinations, we can achieve things like quantum key distribution, quantum teleportation, superdense coding, etc. And all of this will be covered in lecture 3. Yeah. Yeah, Praveen?
Hello.
Praveen?
Yeah. Yes.
Yeah.
So thank you, Dr. Priya. So, as Dr. Priya had earlier mentioned, there's something called a quantum phase. So, if you consider states plus state, the 0 plus 1 state, and minus state 0 minus 1, even though they give the same probabilities on measurements of say, probabilities of 0 and 1 state, they're not the same states. This extra degree of freedom is extremely important and useful, and is a key point in quantum computing. So for a single qubit, we had saw that the point in the Bloch sphere can be represented by two angles, theta and phi. Theta gives the relative amplitudes. For example, for zero state, the cos theta by 2 is the amplitude of 0, the mod square of this. And the sin theta by 2, mod square of sin theta by 2, gives the amplitude of state 1. So whereas we have the extra relative phase due to the complex nature of the state, we have e power I phi. Here phi denotes the phase of the state, the relative phase of state 1 with respect to 0. And so this phase is pretty useful, and we'll see in the following algorithms. So the first algorithm to illustrate this usefulness is the Deuce-Dosha algorithm, which is a generalized version of the Deuce algorithm. So the task over here is to determine if the function, which takes an input of n-bit string and gives an output of single bit, is constant or balanced. So constant function is when for any input, any n-bit string input, it always gives the same output. A balanced function, whereas, gives either state 0 or state 1 for half. So for it gives 0 for 2 power n minus 1 input bit strings and 1 for the others. So classically, we would, if you think about the problem, to determine whether it's balanced or constant, you'll have to give an input of 2 power n minus 1 plus 1. That is one more than half number of possible inputs to determine if it's balanced or not. For example, the worst case scenario will be when all the first 2 power n minus 1 gives me the same value. You might assume that it's a constant function, but if you give the next value, it might turn out to be a balanced function. So worst case scenario, we'll need this many number of evaluations. But using quantum algorithm, we can show that this can be performed with just one use of the oracle. So the oracle action is just a unitary gate, the UF, which is a conditional gate based on the input X. So based on the input X, it adds to the qubit, which is at the state Y. It adds U plus binary addition of f of X. So initially, we create a superposition of all possible input states by applying a tensor product of Hadamard gates, which will give a superposition of all states. And then we apply this oracle followed by another Hadamard gate. Next slide, please. So first, we prepare the input qubit states, the n qubit input states, which is the register qubits, and one ancillary qubit in the state of 1. To create a superposition of all inputs, we apply Hadamard gates on all the register and also on the ancillary qubit because we want a state minus. Now we apply a oracle into U of f, which basically makes it to x comma y plus f of x. So if we observe this, let's see for a single input state x, what happens. So if I just have a state x, I apply U of f. For state in the second ancillary qubit, if it's 0, 0 plus f of x, and I have minus of 1 plus f of x. So if f of x is 0, I'll get the same, I get no difference. But if f of x is 1, the 0 and 1 gets are interchanged, and hence the minus 1 phase is brought outside. So minus 1 power f of x is brought outside, and this is the main use of the phase over here. So thus, when we apply this to the superposition state of all input vectors x, I basically get a superposition which has a coefficient of minus 1 power f of x. Next slide, please. So now let's apply a Hadamard gate on all the input states, input registers x. So Hadamard on input register x basically gives this expression, which you can derive by yourself. Just a minute, finish the algorithm, then answer the question. When I apply the Hadamard gate, I basically get this. You can show this identity. So when I substitute this into the expression, what I obtained is minus 1 power x dot z plus f of x to multiplied by the state z, where z goes over all the input states. So now let's consider the state of just the register 0, register state 0, that is when z is equal to 0. So if z is equal to 0, the x dot z exponent goes to 0, and only f of x remains in the exponent. So if f of x is constant for all input x, so all the minus 1 adds, or minus 1 power f of x, all are same, and they will all add up, and they give 2 power n possible such minus 1s or plus 1s, and the amplitude of 0 will be plus or minus 1. And if the amplitude of 0 is plus or minus 1, the amplitude of all other states should be 0, because a quantum state is normalized. So hence we'll get a measurement, when we measure the state, we'll get a register value of 0. And thus we'll know that it's a constant function. But whereas if it was balanced, for half the input state z, when I sum over x, minus 1 power f of x for half the values will be plus 1 and half the values will be minus 1, and thus cancelling out. And thus the amplitude of 0 will be 0. So hence on measuring we will get any state which is not 0. So this measurement can be used to distinguish between the two cases of the function, and thus we have solved the problem. So to recall, the problem which we aim to solve is to determine whether the function f of x is either constant or balanced. By constant, I mean for all input states, it gives the same output. And by balanced, I mean for half the input states, it gives us 0, and half the input states gives us 1. So you might think it's not very useful problem, but it's pretty useful when it comes to cryptography and for verification purposes. Next slide, please. We had seen one use of the quantum phase. So let's look at another popular use of the quantum phase. So classically, say if you have a deck of n cards, and to search for a single card in this deck, you will have to check every card in the worst case scenario. But using this quantum algorithm called Grover's search algorithm, you can do this search with just root of n checks with the oracle. So the Grover's search algorithm consists of two main steps. One is the oracle creation, followed by amplitude amplification. So the oracle creation first is something like what we did for Dosh algorithm. You have a function f of x w, where w is the target state. So if x is not w, it just gives us 0, and if x is w, it gives us 1. It's an indicator function whether the input state is w. So w is the state which you want to search, by the way. So the quantum function of this f of w can be given by the unitary gate u of w, and which transforms xy state to x y plus f of wx, similar to what we did for Deuce-Rosha. This, when applied to the ancilla minus state, we saw that if the function is gives a value of 1, the phase is brought outside, minus 1. So thus, we'll get a minus 1 phase power fw of x if we apply this unitary gate. So thus, by some mathematics, we can show that this u of w can be written as identity operator minus minus twice of w, the projector to w state. So this ket w bra w is basically a projector to my space of w. So what this does is it adds a minus phase to the state w and leaves the remaining states in the same state by multiplication of identity. So it flips the state of w and does not change the other states. Next slide, please. So we have seen now how to mark the required state w, but now let's see how we can amplify this, how we can get the result. So first we prepare the equiprobable superposition state, the normalized superposition of all possible input states. Basically, making a superposition of all possible cards in the deck. So once we do that, we apply the next Grover's iteration. That is, first we apply the operator ui minus 2w, the oracle step, which marks the required state w. And next we apply the operator u of s, which is 2s, the projector 2s minus I. So if you do some mathematics, so think of let the states psi be a of x times the ket x. A of x is the amplitude of the state x. When you apply u of s, if you try doing the mathematics, what you see is the coefficients become 2 times the expectation value of the amplitudes minus a of x. So expectation of the amplitudes is basically the average of the amplitudes, and a of x is the amplitude of that particular state. So if I write a of x as the expectation, the mean value plus some deviation, I can rewrite this as x, the coefficient 2 times expectation minus a of x can be rewritten as the mean minus the deviation from the mean. So effectively, it translates the state x, superposition state, the marked superposition state, to a state which flips it over the mean of the states. So I will try to show what exactly is doing in the next slide. So after this Grover's iteration, apply some root n times, which you can also prove that root n times is sufficient. So the amplitude of the mark state becomes 1, whereas the other states go to 0. And thus on measurement, we will get the mark state. We'll get the W state with full probability, almost full probability. Next slide, please. So basically summarizing, I first create a superposition of all possible states by applying the Hadamard gates on the input states. Then I apply root n times iterations of the Grover's iteration. And one Grover's iteration consists of the oracle marking, where I add a -1 phase to the mark state, to the required states, which satisfies a property. And then then I flip it over the mean of the states by applying these gates. So next slide. So effectively what it's doing is I prepare the state in all superposition of all possible states. I first mark the state and flip the face of the state. And then I amplify this by flipping over the mean. So the mean is denoted by the dotted lines in this diagram. I flip the states, I flip it over, I rotate it over there. But thus you can see that if it's the mark state, we'll always end up with a larger amplitude. And hence on measurement, we will obtain the mark state with higher probabilities. So if I repeat this process root n times, I can show mathematically that I will always get the mark state with higher probability. Next slide, please. So in this algorithm, you might wonder, like I had assumed that I knew the answer W, then created the oracle to mark the states, right? That's not always the case. I might not know the answer always. So we can create an oracle such that it checks whether the state satisfies a certain property. So this property can be some satisfiability problem, or whether the given input x solves a problem or solves a set of equations or something like that. So if it satisfies that, I can flip it. So these kind of controlled operations can be created and such oracles can be created. So these satisfiability problems belong to it's a type of an NP problem whose solutions are hard to find but are easy to verify. And they can be verified by constructing such oracles. So thus when we have superposition of all possible solution states, the oracle, quantum oracle basically marks the solution states which satisfy this relation. So in the next step, we basically amplify this mark state. So I guess that's it. So if you have any questions, you can ask right now. So you'll be looking more into the Grover's algorithm implementation during the tutorial today. And you can also try out the set problems which cover some topics which I covered today. So thank you.
Yeah, thank you. These are the few references that you can refer to learn further about quantum computation.
If you have any questions, you may unmute yourself and ask now or ask in the message chat box.
Yeah.
Okay, thank you for attending this lecture. Since there's no questions, we can conclude for now. We will have the next lecture at 11:30. There is half an hour from now. by Professor Pradeep Sarvapalli. You can either stay on this call or you can join again later.